Alright, welcome back to another Linear Algebra final review video. This is going to be the part 2 video. In the last video, in the part 1 video, we talked about kind of the beginning stuff that you learn in linear algebra. Right? We talked about linear transformations, we talked about matrix algebra, right? So matrix multiplication, finding the inverse of a matrix, etc. We talked also about determinants and kind of the different methods that we use to find determinants. Alright, so in this video we'll be talking pretty much about everything else that you cover in linear algebra except for the eigen stuff, which will have its own separate video. That will be the part 3 video. Okay, so before we get into the specifics about what we're going to be covering in this video, I really want to make sure that you guys subscribe to this channel. We're trying to hit 1,000 subscribers by May, which is actually now next month, so hopefully we are going to be able to do that. Anyways, let's get into this video. So in this video we'll have 13 problems. We will be starting off by talking a little bit about span, just getting comfortable with that concept. There's not going to be any problems included in the full 13 in that section, but I think it's definitely good to review that. Span is something you have to deal with in things like vector spaces and subspaces, which is the next thing that we'll go over. And we'll do a couple problems there. Then we'll move on to null and column spaces, followed by bases. We'll talk about coordinate systems, okay? And then we'll talk about dimension and rank, and that will lead us into change of basis, okay? Now I do have all the timestamps on the left, but if you are trying to jump right to change of basis, what I would recommend is first going and checking out the coordinate systems video, or the coordinate systems problems, because that is kind of the prerequisite to understand change of basis. So if you're not understanding change of basis, you most likely are confused about something in the coordinate system section. Okay. So with that being said, let's move on to our first section, that being the span section, and we are going to try to find the span of these two vectors 1, 0 and 0, 1. Okay, and I'm going to label these guys, and that's the highlighter, not the marker. Here we go. So I'll label these guys. We have 1, 0 and 0, 1, and I'll graph them. 1, 0 is over here, and then 0, 1 is up here. Okay? Now, what the span of vectors are, right? It's kind of the set of all possible linear combinations of the vectors in the span, right? So what does that mean? Well, here, right, like first off, what is a linear combination? Well, an example of a linear combination is like 2 times the vector 1, 0 plus a 3 times the vector 0, 1. Right, so that's an example of a linear combination. Now we're saying, okay, what about all the possible linear combinations? We put an A here and a B here. Okay, and we're trying to find the set of all of these possible linear combinations. What does that represent here? Well, here it's the xy plane, right? You can linearly combine these vectors to give you anything on the xy plane. Okay, you can get 3, 3, you can get 6, -2, and things like that, right? So that's the idea of what we're talking about with span. Now we'll try this again with another problem. Here we have, and I already underlined these, so we have -1, 0. And we have 0, -1. Oops. Okay, so there's 0, -1. Now, what's the span of these two vectors? Right? What's the set of all linear combinations of these two vectors? Well, again, you can probably see that these are kind of just the basis vectors rotated, right? And so we can these are basically the same thing as the basis vectors. We can describe the entire xy plane again with these two vectors. Okay, so again, the span of these two vectors is the entire xy plane. Okay, and that's the idea with span. So now we're going to move on to our first question of this video, and that's going to be on vector spaces and subspaces. Okay, now that is labeled as question number 13 because it's going off of the last video, which was ending on question 12. And this question is asking, we have two vectors v1 and v2, and they're in a vector space V, and we're letting h equal the span. See, the span's popping up again, right? The span of v1 and v2. Okay, so h is all the possible linear combinations of v1 and v2. That's what that means. And this problem is asking us to show that h is a subspace of V. Okay, so before I get into the criteria for subspace, I want to talk about what a vector space and a subspace actually are. Okay, because this is something that I definitely was confused on when I was in linear algebra. Okay, so let's take, for example, a vector space V that's in R3. Okay, R3 is an example of a vector space because it is a place where vectors can occur. Right? That's a very simplistic way of putting it, but it gets the point across. You understand what I'm talking about, right? R3 is a place that can hold vectors. Now, another example would be, you could describe P2. I don't know how you can maybe put it like that, right? So we're talking about polynomials, which would also be three-dimensional. Right? This is polynomials up to degree 2, so we're kind of talking about like x squared plus x plus 1, right? So we have an x squared term, a x term, and a constant term, right? So you would have each of those on their own axes. So that's another example of a vector space. Okay, and that's definitely one that you end up seeing, right? The main two are, like an R3, right, where you have like x, y, z, or something like that. Or you might have like a polynomial space, which is also very common. So we have this vector space R3. What is a subspace of R3? Well, if we label these as x1, x2, x3, right, our axes, the x1, x2 plane qualifies as a subspace. Okay? This is a subspace, okay? And why is this a subspace? Well, basically, you have that the x1, x2 plane is a subspace because the zero vector, okay, of R3 is in the x1, x2 plane, right? And the x1, x2 plane is also closed under vector addition. Think about it. There's no z component, right? Or there's no x3 component. So if you add two random vectors in the x1, x2 plane together, you'll get another vector in the x1, x2 plane. If you do, it's also closed under scalar multiplication, right? That's our third point. Okay, so if you have some vector in the x1, x2 plane and you multiply it by a constant, you'll get another vector in the x1, x2 plane. And that is the criteria for something to be a subspace of a vector space. Okay? So, with that being said, we're able to move on to our actual problem, which is to show that H is a subspace of V, where H is the span of V1 and V2. So let's start off with our first criteria, right, which is that the zero vector of V is an H. Well, we can figure that out pretty simply because we can just multiply 0 times both vectors, right? That works because H is the span of V1 and V2, right? So it's all the possible linear combinations, and that includes when you have a 0 as the coefficient in front of V1 and V2, right? So that works. Now what about being closed under vector addition? Well, let's pick two arbitrary vectors. And to ensure this, what we're going to do is define two new vectors, A and B. Okay? Make that look a little nicer. And these are just going to be linear combinations of V1 and V2. Okay? Now, to give you a reason, why are we including like the S1, the S2, the T1, T2? Why are we doing two new vectors? Why are we not just adding V1 and V2 together? Right? We're doing this in order to more easily show that we can take any vectors in the span of v1, v2, right? We can take any vectors in this span, and we can add them together and get another vector that's in the span of v1 and v2. All right? If you think about it, it starts to make sense, right? A and B could be any vectors in v1 and v2. Okay, it's just an easier way to show that. So if we add these two vectors together, a plus b, we get s1 v1 plus s2 v2 plus t1 v1 plus t2 v2, which we can simplify to be s1 plus t1 times v1 plus s2 plus t2 times v2. Okay, now this checks off, but why? This checks off because s1 plus t1, right? These are both constants. So you add them together, you get another constant. Same thing happens for s2 plus t2, right? You get a constant. So you get a linear combination of v1 and v2 as your answer, right? Which makes sense because that's in the span of v1 and v2. So that works, right? H is closed under vector addition. And we can move on to our last criteria, which is to prove that H is closed under scalar multiplication. So let's just multiply A. We'll multiply the vector A by some constant C. What do we get? Well, we get C times S1 V1 plus S2 V2, which we can write as C times S1 V1 plus C times S2 V2. And this checks off. Why? Because CS1 is still a constant, CS2 is still a constant. All right, and you're multiplying that in on V1, V2. That's just a linear combination of those two vectors, and that would be in the span, right? Because that's the definition of what the span of these two vectors means, right? So since all these three criteria are met, we know that H is a subspace of V. Okay? So H is a subspace of V. Okay? And that is not how I would write that on a test. How on a test I would just say H is a subspace of V because the zero vector of V is in H. H is closed under vector addition, and H is closed under scalar multiplication. That's how I would write that out. You would write out the three criteria in your answer. I just want to move on to the next problem. So now we're going to move on to our next problem, which is on null spaces and column spaces. Okay, this is problem 14, and it's asking to find the null space of A, which is a 3 by 5 matrix. Now, what actually is a null space? Okay, that's probably the initial question that you should be asking, because if you know what a null space is, you'll understand more of how to find it. Okay, the null space, to describe the null space, let's just say that we have a linear transformation that's transforming vectors from R3, okay, and it's transforming them again into R3. We'll keep it simple here. Okay, and let's say that we have this line of vectors here. Okay, so it's a line of vectors that just connect to this line, right? So these vectors describe that line. And let's say that when we do our linear transformation, okay, what color goes good with orange? Let's go blue. Okay, so when we do our linear transformation, all of the vectors on that line go to 0. Okay, they all become 0. Okay, so the null space, okay, of this transformation matrix, okay, so null of A is the. So how we're going to find this actually is we're going to have to row reduce here. And so I'm going to start off by just swapping rows. Okay, because I want to get that 1 in the first pivot. Okay, because that's just going to be a lot easier to deal with. Okay, so I've finished swapping rows, and what we're going to do now is we're going to augment this matrix with zeros, and we're going to row reduce, because what we're trying to find here, okay, is we're trying to find the vectors, right, the span of vectors that will go to 0 when the linear transformation is applied. Okay, that's why we're doing this. So, row reducing here, I want to get, first off, I want to keep the first row the same. And these zeros, no matter what we do, these zeros will stay zeros, because you can't multiply a 0 by anything and add it and have it be anything other than 0, right? So what we're going to do here is we're going to make these two things zeros. We're going to make the entries in the first column under the pivot 0. And to do that in the second row, we had to multiply the 1 by -2. And we got -2 off of that. We add it to the entry in that row, and we get 0. So that gives us our 0 here. Now we'll do that for the entries across the first row. So we'll start off with that -2. Multiply by -2, get 4. We subtract by the 4 that's already in the second row, and we get 0. So we get a 0 here. We can do that for the 2 in the first row. We get -4. We add 5, we get 1. We can do 3 times -2, get -6. We add 8, we get 2. And then lastly, we have a -1 times -2, we get 2. Subtract 4, we get -2. Okay? I'm assuming that you guys are, comfortable with row reducing, so I am trying to go a little bit quicker. All right? So now for the third row, we have to multiply by 3 and add. So we can do -2 times 3 is -6 plus 6 is 0. We'll have a 2 times 3 is 6 minus 1 is 5. We'll have a 3 times 3 is 9 plus 1 is 10. And then we have a -1 times 3 is -3 minus 7 is -10. Okay? Now as you can see, this third row is a scalar multiple of the second row. So what we're going to do is just zero the third row out, right? Okay, and now that we've done that, we actually only have one more step left, and that's to zero out. We have 2 pivots at this point. We have 2 non-zero rows left, and so we have 2 pivots. Now what we have to do is just get the non-zero entry above the second pivot to be 0, and then we're done row reducing. Okay, and we can actually go and create our span. This is that entry that we have to deal with, because this is our pivot. 1, -2, 0. And by the way, I know that these 2 entries will stay as 1 and -2 because these are zeros, and when you do any transformation, the zeros won't make a difference, right? So to get this thing to be 0, we had to multiply the 1 by -2 and add. So we can apply that for the rest of the entries. We have a 2, this 2, times a -2, get a -4, we add on to 3, we get -1. Then we have a -2 times -2, we get 4, we subtract 1, we get 3. Let's call this column x1, we'll call that x2, x3, x4, and x5. Okay, and we know that this solution vector, this x, is equal to these vectors represented as a column vector. right? So what is x1? Well, x1, first off, it's not a free variable, right? Our non-free variables are x1 and x3. So those are going to be described in terms of the free variables, which is x2, x4, and x5, right? So x1 is going to be equal to 2x2, right? We flip the signs of all of them because they'll get added or subtracted to the other side. We'll have plus x4, and then we'll have minus 3x5. For x2, that's a free variable, so we're just going to write it as such. For x3, that is a non-free variable, okay? So it'll be equal to negative 2x4 plus 2x5, and then x4 and x5 are free. So we just write their own values down. So we're going to break this up and write this as x2 times 2, 1, and x2 is not present in these vectors, or in these guys right here. So we'll just put them as zeros, right? Because x2 doesn't appear there. And we'll do the same for x to the 4, or well, x4. So we'll get 1, 0, negative 2, 1, 0. And then we'll do the same for x5. Negative 3, 0, 2, 0, 1. Right? And where I'm getting all those numbers from, for x5, negative 3 right here, there's no x5 here, there's a 2 there of x5, so that's the 2 there. There's no x5 here, and there's 1 x5 here. Okay, so that's where those come from. Now, the span of these vectors that we just found, this one, and this one, that's our null space, right? Because the linear combination, okay, the linear combination of these vectors, okay, any linear combination, will go to 0 when you apply the transformation. Okay, and we describe that space, okay, that space in R3. It doesn't have to be a line. It could be a plane. It could be the entire R3 maybe. I don't know. Like, I'm just kind of putting some examples out there, right? And this entire space goes to 0. Okay, so we describe it with a span. That's the null space. So now moving on to problem 15, we're talking about the column space. And we want to find a matrix A where the column space of A is this mess. Okay? So we have to understand what a column space actually is, right? The null space of A, okay, is the set of all vectors that go to 0 when you linearly transform them with that matrix A. Okay, the column space of A is all of the possible linear combinations of A. Okay, so that, and to describe that, right, let's say we have the matrix equation AX equals B. Let's say we have an A that's 1, 2, 3, 4. Okay, the column space of A, okay, is basically represented by all of the possible B's that you can get here, right? Because it's represented by all of the possible linear combinations of A, right? And well, what do we mean here? Why does that make sense? Well, when you multiply, when you perform this operation AX, you get, let's say that X is X1, X2, right? So you get X1 times 1, 3 plus X2 times 2, 4, right? This here is all of the possible linear combinations of these two vectors, right? Because we can put any x in there. Okay, so that gives us like infinite freedom, right? We can get all of the possible linear combinations. Okay, so basically how we represent the column space is by a span of the columns of A, right? So if we have a matrix 1, 2, 3, 4, okay, and we say that's matrix, let's just get away from A. Let's say this is B. the column space of B equals the span of 1, 2, and 3, 4. Okay? That is what we mean with column space. Okay, so it's all the possible B's that you can get. All right? Now this doesn't look like, we're already defining the column space. We're already saying what the column space actually is. But before, you've seen that I had the column space defined as a span. Well, here, this is kind of like a span worked out a little bit. Okay, and now I gotta go erase this stuff again. Okay, hang on. Erasing. Good. So in the last problem, we had the x vector described similarly to this. Okay, but then we broke it up and formed a span. Right? So this is kind of like an alternate form. That's kind of how you can think about it. Right? Because we can break it up and say that the column space of A equals A times 7, 1, 0 plus B times 5, negative 1, 2. Right? This is just how many times B appears in each row. Okay, and this is how many times A appears in each row. So we can now write the column space of A as the span of these two vectors. Right? And maybe if that didn't make sense why we did that in the last problem, it's because A and B here could be anything, right? They could be any value. They could be 1, 2, 3, 4, 5, anything. So we can write that as a span. That's how we can illustrate and eliminate those variables. Okay, so that's why we're doing this. Hopefully that starts to make a lot more sense to you. Remember how I said that the column space of A is the span of the columns of A. So if it's the span of the columns of A, if those two vectors are the columns of A, we can just now write this as 7, 1, 0, 5, negative 1, 2, and be done. Right? That was the idea with this problem. So hopefully that makes a lot more sense now. We're talking about what the column space of A actually is, right? It's the span of all the possible linear combinations of A, giving you every single B vector that you could get. Okay? That's what this column space is telling you. So moving on to problem 16 on bases, we have that if V1 is 1, 1, 3, V2 is negative 2, 1, 6, and V3 is 2, 0, 6. Is V1, V2, V3 a basis for R3? Okay, so first we have to talk about what is a basis, right? What's a basis for R3? Well, an example of a basis for R3 is just the standard basis, right? We can just use that. And basically, let's kind of just write that out real quick here. Okay, it's the vectors. We have, that point 1, 0, 0. We have 0, 0, 1, and we have, and that's actually, I usually draw that as the y-axis, so I'll do that, and then say this is 1, 0, 0. Okay, these vectors form a basis for R3. Why? Because they span R3, right? You can take any linear combination. Okay, and if you take all possible linear combinations, they can describe any point on R3, or in R3 rather. Okay, so that's the idea of a basis. They span R3, so they're a basis for R3. Okay, so in basically what that means is you can use them as building blocks in a way. Okay, maybe that's another way to think about it. So I'm just trying to give you alternative ways. Now, here's the idea. If we put those vectors into a matrix, right? So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. They are linearly independent, and that is characteristic of any three vectors that will be a basis for R3. They will have to be linearly independent. If they're not, all right, let's say we had 1, 0, 0, 0, 1, 0, and then this column got zeroed out. Okay, this would be linearly dependent, and so it would not be a basis. Okay, so that's the idea here. So what we do, we put these three vectors, 1, 1, 3, negative 2, 1, 6, and 2, 0, 6. We're going to put them in a matrix and row reduce. Okay, So first off, we can see here that it would be best to scale down the third row to 1, 2, 2, right? We can divide by 3. And then we can more easily row reduce by just zeroing out the pivots below, or sorry, the entries below the first pivot. Okay? And we'll keep the first row here. To get this entry to be 0, we just had to multiply by -1 and add, and the same thing for the third column. So multiplying -2 by -1, we get 2. We add 1, we get 3. On the same token, if we added 2, we would get 4. So we know that right here is going to be 3, here is going to be a 4. For 2 times -1, we get -2. And we add 0 to get -2. And if we add to this 2, -2 plus 2 is 0. So we get a -2 and a 0. If you zero out this entry here, okay, then you'll actually get a non-zero entry here. So this isn't, all hope is not lost yet. This still could be linearly independent. Okay, I would get this to row echelon form before you make any decisions. Okay, this is not yet in row echelon form. So what I'm actually going to do, and even to further prove this here, let's prove this in another way. I can swap rows here, and I'll scale down 0, 4, 0 to get 0, 1, 0, and voila. I made a row swap, and I no longer have a 0 entry here. So there's another way that I could have done it. Okay, so the last thing that I have to do here to get this into row echelon form, right, so we can see if this is linearly independent or dependent, we can zero out this entry here. How we do it? We multiply by -3 and add. Okay, we multiply row 2 by -3, we add on to row 3. If we do that to this entry here, we would still end up getting -2 because this is a 0, so it doesn't do anything. And we end up with 0, 0, 1. We can scale that down, and we have a linearly independent matrix. Now you can put this into reduced row echelon form. It honestly doesn't matter at this point, and it's kind of whatever makes you feel better. I was always put these in reduced row echelon form because it just made me feel a little more comfortable, right? But from this, you can literally just say this is linearly independent. Therefore, you can say that V1, V2, V3 is a basis for R3. Okay, and that does it for problem 16. So moving on to our next basis problem here, number 17 is asking us to find a basis for the column space of A, with A being a 3 by 3 matrix. Okay, so we now want to find a basis for the column space. Okay, so basically what this means is that maybe one of these vectors, okay, in A, right, one of these column vectors are useless. Right? Remember what the column space of A actually is. Okay? The column space of A, the column space of A is all the possible linear combinations of the columns of A. Right? All the possible linear combinations of the columns of A. So it's basically all the possible values of B, of the vector B, right? In the matrix equation AX equals B. So maybe we can still describe the column space of A without using one of these vectors, right? Because maybe we can still attain all of these possible B vectors with just two of these column vectors of A. That's what we're finding here. So all we have to do is row reduce this and see, well, is this linearly dependent, right? So basically the same exact process as the last problem. So we zero out the entries under the first pivot, and we do that first by, we multiply the first column by -1 and add. Okay, so we multiply by the first row by -1 and add, and so we get a 1 and a 2 here. Okay, and then we multiply the first row by -2 and add to get the third row. Okay, and that will zero out the third row, and so you have something that's linearly dependent. So what you can do is you can take this and you can see that this vector is garbage, right? Because it's linearly dependent, right? So you could say garbage, okay, and throw it out. It doesn't matter anymore. So we can just cross this vector out, and we can say that the basis for column A, column space of A, is equal to, and we'll just have 1, 1, 2, and 1, 2, 3. Okay, and those are the original vectors, right? All we did here was we just found that the third vector here was useless. Okay, so this is the answer to problem 17. All right, so let's move on to problem 18, which is on coordinate systems. And we're given that the basis B is B1, B2 for R squared, where we define B1 as 1, 0 and B2 as 1, 2. And it's asking if the coordinate vector relative to B is -2, 3. It wants us to find x, okay? So what I think really would have helped me when I was in linear algebra was knowing that whenever we were given a basis, and this is something I don't think I fully understood. We're given a basis without anything here, okay? This is relative to E. So this is basically saying, okay, here's what B1 and B2 are relative to your standard basis, right? That's what this E means. Now, what is the standard basis? Well, the standard basis for R2 is 1, 0, 0, 1, right? It's our regular standard basis, right? So our regular graph paper has the standard basis. Okay, and it's saying if x of b is -2, 3, then what's x relative to e, right? To the standard basis. That's what we're trying to find here. Okay, so that's how you need to image this. It gives us what x relative to b is. We need to find x relative to e. Okay, so that I think would make the problem a lot easier to look at. All right, but it's kind of just implied that when you don't have anything there, it's relative to e. Now be careful that doesn't apply for this here, because you can see here context matters, because it's saying if x relative to b is this. So this is relative to b, right? This is moving -2 in the B1 direction and 3 in the B2 direction. So that's what this means. It's not relative to E, or else we'd already have our answer, right? Because this is what we're trying to find, is x relative to E. Okay? So, actually going into this here, how do we encounter a problem like this? Well, what we do is we have this formula, PB times x relative to B equals x. And again, this is relative to E, right? Or, well, they usually write it within like an epsilon looking thing. Okay, so that's the formula that you need to be using here. But I need you to understand where this comes from, because you're going to have a lot of things to remember for this test. Okay, so it's not going to help you at all for me to just say, okay, here's the formula, now go use it. The idea here is that this change of coordinates matrix PB, a better way of writing this, and how we'll write it in the change of basis section, is it's going to transform a vector with a relative to b to a vector relative to the standard basis. That's its job. And basically the intuition behind that is that you were given, how we're able to do that here is that we were given our B1 and B2 vectors relative to E, right? So if we put this thing in a matrix, right? So let's say going from B to E, and yeah, that's just how the arrow is. It's kind of weird, right? I know. we say that this is equal to, the matrix becomes 1, 0, 1, 2. Okay, now you have two vectors that will take something relative to B and convert it to something relative to E. Okay, so that's why these are so nice. If you had your two standard basis vectors being described as B1 and B2, right, or as relative to your basis B, then it would be flipped, right? Then it would be the change of coordinates matrix from the standard basis to basis B. Okay, so anyways, we're going to multiply this by xb, which we know to be negative 2, 3, and that's how we're going to get x relative to E. So we get negative 2 times 1, 0, plus a 3 times 1, 2. Okay, we know that that is negative 2, 0, plus 3 times 6, which gives us a 1, 6. And that right there is x relative to E. Okay? So that's how you do something like that. So moving on to problem 19. This problem says let a basis B equal 4, 5, 3, 4. If x equals 15, 8, then we want to find the coordinate vector of x relative to B. This is actually the exact same problem as we previously had, except for, well, actually, let's start with the similarities first. This is still B1, and this is B2. And both of these vectors are relative to E again, right? They're relative to the standard basis. You can write it just as we wrote it in the last problem, right? If these are relative to E, you write the whole basis like this, okay? And we're given x relative to E, and that's the difference here. We're given x relative to E. We need to find x relative to B. So writing out our formula here, we have P from B to E, right? That's how we can write our change of coordinates matrix. And we multiply that by some coordinate vector, some coordinate vector relative to B, and that's equal to some coordinate vector relative to E. Okay, what we can do here to make this a little nicer, first off, we could actually just augment this change of coordinates matrix with xe, right, and then solve for xb that way. We could absolutely do that, right? But how we can also do it, and I'll show you this way. If we multiply this by P to the B to the E inverse, okay, and we multiply this side by the same exact thing, we can come up with another equation, which will actually make a lot of sense. And I'll show you why. Okay, and this actually leads into the change of basis stuff a little bit, so I'm kind of working ahead, but you'll see here that this is xb, right, because this becomes the identity, and this is equal to the P inverse of BE times xe. Okay, now here's what's interesting, and here's what we'll talk about in change of basis, which what I'll mention. Okay, this thing, and it makes sense to actually write it as P from E to B rather than P inverse from P to E, right? They're the same thing, but if we write it like this, well, this is the exact same equation. This is kind of arbitrary, as as the equation that we had before of PB to E, XB equals XE. If you just flip around the E's and the B's here, you get this exact equation with these two things. Okay, so it's actually a nicer way of writing it, but so you end up getting that if you invert the change of coordinate matrix from B to E, you get the change of coordinate matrix from E to B. And that's the idea from this. Sorry if that was a little disorganized. I got a little too excited, I think. So anyways, P from B to E equals 4, 5, 3, 4. So P B to the E inverse equals, we still have those 4's, and we just negate the kind of reverse diagonal. Okay, and so now we have that matrix. We can multiply it by xe, which we know to be 15.8. Okay, and so this is p from b to e inverse, and this is xe. Okay, you can also write this as p from e to b. All right, and now we're going to get what xb actually is. So we have 15 times 4, negative 5, and we're adding 8 times negative 3, 4. And all right, well, let's see what we can get here. Well, first off, this will be a 60, negative 75. And then we have plus, this becomes a negative 24 and a 32. And now we just got to add these things together. Okay, so we end up getting a 36 here. And right here, this is going to be a 75 minus 32 is 43. And we make that negative. That's actually how I'm sure that's how you guys think too, but like that's how I got through having like larger negative numbers and then like having to add a number to it or something like that. Like that's how I actually did that back in like grade school. So anyways, enough about my life story. That is the answer to this problem. All right. So for problem 20, we're going to shift our focus to dimension. This problem says let V be a vector space and find the dimension of V where V is the span of 3 vectors. So to better understand this concept here, just because we have the span of 3 vectors does not mean that we're now talking about a 3-dimensional space. We could have the span of 3 linearly independent vectors, okay? And that will definitely be 3-dimensional. But if these are linearly dependent, these vectors, okay, and we're taking the span of that, so let's say we have something like 1, 0, 0, 2, 0, 0, and 3, 0, 0, right? Let me actually write that down so you can see what I'm saying. Okay, if we have the span of these 3 vectors, these 2 vectors are redundant, right? We're still going to be spanning just a line, right? And that's all that this is going to be. This will just be a line. This will not be 3-dimensional. This will be 1-dimensional, in fact. Okay? So the span of these 3 vectors could be a line, it could be a plane, and of course it could be all of our 3. But we need to figure that out by row reducing here. Okay? So we need to see if these guys are linearly independent or if they're dependent. And if they're linearly dependent, to what degree are they linearly dependent? So we're going to go through the first step of row reduction here, just zeroing out the entries under the first pivot. And to do that, well, we had to multiply the first row by -2. And add on to the second row. Okay, so that gives us -8, and then plus 5 is going to be -3. Doing the same exact thing, we have a 7 times -2 gives us -14, plus 8 gives us -6. Then we move on from getting our third row to be zeroed out in the first column. We have to multiply by -3. So we do have a 4 times -3 is -12, plus a 6 is going to give us -6. And we have a 7 times -3 is -21, plus 9 is going to give us -12. Now here you can see that the second row is a scalar multiple of the third row is a scalar multiple of the second row. Of course, vice versa, but to make things easier, what we'll do is, first off, we'll reduce this second row to make it look a little nicer, just because I want to do that, and then we'll zero out the third row. Here, we now have something in row echelon form. Okay, we have our 2 pivots, okay, and everything else is, we don't really care about that. We can just zero that out, right? And here's more of the intuition by why we can already assume that this is linearly independent. Okay, we can zero this value out, right? And that won't change this because this is a 0 here. It will change this because it's a 2 here, right? But that doesn't matter, because what's going to happen in the next step is once that's zeroed out, we just have a free column, okay? This doesn't matter. None of these values matter here because there's no pivot in that column. Okay, so it's just a free column. It doesn't matter. We can already see that this is in, since this is in row echelon form, we can say that these are linearly dependent and that we have 2 pivots, so the dimension of V is 2. Moving on to problem 21, we have a 3x5 matrix A, and we want to find the dimension of the null space of A and the dimension of the column space of A. Now, this is actually a matrix that we dealt with in problem 14. Okay, and so it may look familiar. I'll actually go back up and show you that right now. So we've already row reduced this and found the null space. Okay, that was this problem right here where we had to find the null space of A. Okay, this is the same matrix here, and we row reduced it, and we got to this point right here. Okay, now we already saw what the dimension of the null space was. Okay, spoiler alert, there's 3 vectors. Okay, and these are, using this method, these are all linearly independent vectors. Okay, and you can verify that if you'd like. Okay, but we see that the dimension of the null space is 3. Okay, but I copied that matrix anyway, so I can show you that. Okay, here's something interesting, and we'll talk about this a little bit more with the rank theorem. Okay, what we have right here is we have 2 free columns, okay, and we have, 2 non-free columns and 3 free columns, okay, and we can kind of take away this augmentation with 0 here, because that doesn't matter, okay. Now, we have 3 free columns, so that means that the dimension of our null space is going to be, and this is usually only 1L, that means that this is 3. And since we only have 2 columns that aren't free, we get that the dimension of the column space is actually 2, right? That goes back to when we found the basis for a column space, right? We had a matrix A, we row reduced it, we found that one of these rows was free, it was a non-pivot column, okay? And so basically, one of these columns was free. That's where I messed up. Yeah, one of these columns was free. And so we know that this basis only has 2 vectors in it, right? The other vector is garbage, okay? And so this dimension of in this case as well, the dimension of the column space is 2, right? It's how many vectors are in your basis. Okay, that's another way of putting it. So that's how we got this answer here. Okay? All right, so for problem 22, now we're going to be talking about rank. Okay? So we want to find bases for the row space of A, the column space of A, the null space of A, and we want to verify the rank theorem for a 3x3 matrix A. Now, I have the rank theorem listed below, but we have a more pressing issue. And that more pressing issue is, what the heck is the row space? We have the column space, the null space. Now we have a row space. What is going on, right? So the row space of A is basically just all the possible linear combinations of the rows of A. Okay? It's not the column space, but it's very close to the column space, which is all the possible linear combinations of the columns of A. Okay, so that is the idea there. Okay, so now let's just start row reducing this matrix, and the row space is just going to pop out. Okay, and well, we already have the row space of A, right? We can already find that here, right, by just putting the columns. We span the rows of A, right, and that's the row space. Right, so the row space of A here is just the span of, you could do, 1 3 1 3 1, and you have 3 9 1, and etc., right? So that's the row space, just to show you that, right? But now actually finding a basis for it, we need to see, okay, well, what rows are garbage? Okay, and that'll also lead us to finding the basis for the null space and the column space as well. If we zero out the first two entries under the pivot, the first pivot, we keep our first row and our second row. To get that zeroed out, we need to multiply the first row by -3 and add on. So we have a 3 times -3 plus 9 is going to equal 0. We have a 1 times -3. That gives us -3 plus 1 is -2. We have a, to get our third row to have a 0 in the first entry, we need to multiply the first row by -2 and add on. So we have a 3 times -2 is -6 plus 6 is 0. And we have a 1 times -2 is -2 plus 1 is -1. So now you can see that the second row and the third row are scalar multiples of each other. So we can just scale down the second row and zero out the third row. Okay? In which case, we have this thing in row echelon form. Okay? So we can now find the row space, right? The basis for the row space, rather. Okay? And we can actually use this matrix. We don't have to go back to this matrix like we did with the column space. And there is, like, you can look at that stuff like more in depth if you want to. I'm sure you can look at, like, there's a theorem in your textbook, most likely, if your textbook covers row space, which will tell you that you don't have to find the basis of a row space, you don't have to actually go through and go back to your original matrix and then use that original matrix. It's row equivalent to your, if it's row equivalent to your final matrix, okay, which it is in this case, right? That means that, okay, we can use this as a basis as well, and it's fine. It's the same thing. Okay, so we can say that a basis for the row space of A equals 1, 3, 1, 1, 0, 0, 0, 1. Okay, that's a basis for row A. Now, a basis for the column space of A. Here we can still do the basis for the column space of A, but we do have to go back up to the top and use this column and this column, because the middle column we found out was linearly was a free column. So we have 1, 3, 2, and 1, 1, 1. Okay, so we have a basis for the row space of A, we have a basis for the column space of A. We need to find a basis for the null space of A, and that's going to require us to find the actual null space, right? Because the null space of A is, well, how we're going to find it using this method, the method that I used earlier as well, that gives us the basis, right? Because all of those vectors are linearly independent, and so it's a basis for the null space as well. None of those vectors are garbage. Okay, so all we have to do here, since we have this in a row echelon form, is we just need to get it into reduced row echelon form. And so we can zero this thing out without any effects. Okay, and so now we have that your vector x, okay, will equal, well, x1 is just going to be -3 x2, right? If we call this x1, x2, and x3. You have your middle vector, which is free, and you have your last vector, which is just going to be 0, I guess. Yeah, it would just be 0, right? So because here's why. Yeah, it's definitely 0. Here's why. I was confused at first, but hang on. You augment this with 0 to find the null space. And so here you just get the x3 equals 0, and that's what you just put in here. Okay, so here you just end up getting x2 times negative 3, 1, 0. And then that becomes, so the null of A equals the span of negative 3, 1, 0. Right? So basically all the possible linear combinations that you can get by just multiplying that vector by stuff. Or well, so it's not like a linear combination necessarily. You're just multiplying that by that vector by stuff, and you just get a giant line. Okay, that's essentially what happens there. So that's kind of the span of this thing is just a line, right? Like I talked about earlier in the video, so the span of 1, 0, 0, and I had like 2, 0, 0, and 3, 0, 0. Well, that just is the same thing as the span of 1, 0, 0, which would be a line, right? So, anyways, we can say that the basis for null A equals negative 3, 1, 0. Okay, that can also serve as a basis. And so now we have the basis for the row space, the column space, and the null space. What else do we have to do? We have to verify the rank theorem. So we have that the rank of A plus the dimension of the null space of A equals n. And that is the rank theorem. Okay? Now the rank of A. The rank of A is the dimension of the column space of A. That's just, it's like a fancy word for it in a way. Okay? So we can basically, if we find the dimension of the column space of A and the dimension of the null space of A add up to be n, we verified the rank theorem. Okay? But if you remember in the last problem, it was exactly that, right? Here's n, right? This is an m by n matrix. That's what's meant here. That's a terrible curly bracket, by the way. That's what I was trying to do. So to stop embarrassing myself so much, I'll just do that. Okay? Here, the dimension of the null space of A is 3. The dimension of the column space of A, aka the rank of A, is 2, and that adds up to be 5, which is what n equals here. So all we're doing is we're doing the exact same thing here. The dimension of the column space of A, there's 2 vectors here, and that's also called the rank of A. Right? So that is 2. The dimension of the null space of A, which apparently doesn't have a fancy name, but the dimension of the column space does, whatever. This equals 1. And well, how many columns are there in this? There are 3. So you know that since n equals 3, 2 plus 1 equals 3, 3 equals 3, bam. RT verified. Okay, so we have all 4 things now. We can circle this, and we can circle this, and we have that the rank theorem was verified. Okay, so that is all for problem 22. So now we're going to move on to the final topic for this video, and that is change of basis. Now this is something that I had so much more trouble with than I should have when I was in linear algebra, because it, you know, while I believe I said in the beginning of the video that it was a difficult topic, it really is actually kind of straightforward when it comes down to it. And it's just, you know, getting that right explanation so it makes sense in your head. I think that's a big part. So anyways, let's get into problem 23. So in P2, which means you have polynomial space with like up to degree 2, okay, which is like x squared plus x plus 1, right? That's in P2. All right, and you have B, a basis B, which is 1x x squared, and you have a basis C, which is 1 plus x, 1 minus x, 1 plus x squared. And we want to find the coordinate vector of 15 plus 20x relative to C. Okay, well, since B is a basis for P2, essentially, right, 1x x squared, this is going to be really easy to write 15 plus 20x in terms of B, right? So we can say that 15 plus 20x relative to B is 15, 20, 0, right? Because there's no x squared part. Okay, and well, there you go. That's not the hardest part of this problem, but it's one of the hardest because it's the initial step, right? Starting the problem is always probably one of the hardest parts of the actual problem, right? It's in most cases it is. But anyways, let's get back into this. Enough of me just talking nonstop. Anyways, let's bring up that formula that we talked about in the change of coordinates section. We're going to have some change of coordinates matrix. We want to change coordinates of B to coordinates of C relative to B to relative to C. And we're going to multiply that by a coordinate vector relative to B because we're changing it to a coordinate vector relative to C, right? So that's an easy way to kind of remember that. Now, we need to find this change of coordinates matrix, which is probably the hardest part of the problem, okay? Because it's just, how do you actually go about doing that? Well, here, all you have to do actually is just have a matrix, okay? And you're going to basically augment C with B, okay? And I'll show you what I mean. So if we write C, right, relative to the standard basis, we get 1, 1, 0, right? That's 1 plus x. 1 minus x is 1, negative 1, 0. And 1 plus x squared is 1, 0, 1, right? And if we write B on the other side, we get 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? And the reason why I wrote those in this order is because now we have C to B. That's how I remember it, right? So we're trying to find P of B to C, and so we write it that way in the matrix. Okay, so here's the deal. When we get this thing to be an identity matrix, we will get P from B to C on this side. Okay, that is the idea. Okay, right now, since we actually have the identity matrix on this side, we have P from C to B on this side, which is kind of interesting, right? So we could actually take the inverse of this thing, and then we would have our P from B to C. And how do we find the inverse of a 3 by 3 matrix? We do exactly this. Maybe that can start to, ring a couple bells, okay? So it kind of is fitting that we do this. So now what we're going to do is, first off, I'll zero off, make sure both entries are zeroed off below the first pivot. The first row stays the same. And the third row will actually stay the same as well because we don't have to make any changes to that. To get the second row to be 0 in the first column, we need to multiply by -1 and add. So if we do that for the second row, we get a -2 here. We're going to get a -1 here. We get a -1 here. We will have just 1 and 0 there. Okay? Hopefully you could follow along with that. If we now so we have our 3 pivots located, right? We have our 1, -2, and 1. So I guess what we could do here is just scale down that -2 to be a 1 and get, well, let's actually just make sure that our third row stays the same in our first row. Great. So let's make this a 1. That means that this is to become a 1/2. This is to become a 1/2. This is to be a -1/2, and this is to be a 0. Okay, so fractions sadly will come into play here. I know. It sucks. But we're going to do this because we're champions. God, shut up. Stop talking. It's bad enough when you have to tell yourself to stop talking. But anyways, what we're going to do now is we're going to zero out this entry. So actually in that case, I'm getting everything rid of getting rid of everything there. I don't know what I'm doing anymore because I'm just talking about dumb stuff. But if we zero this out, we have to basically multiply row 2 by -1 and add. So we get a 1/2 here. We multiply this thing by negative, so yeah, 1/2 there. And then multiplying this by -1, we get a 1/2, adding it on. And then we get a 0 here. Okay, and the last thing to do is zero off the third column except for the pivot. We get 1 0 0 0 1 0 0 0 1, and then we'll still have a 0 0 1 here. We will have, to get this thing to be 0, we need to multiply this 1 by -1/2 and add. Okay, so that doesn't actually change anything in the two first columns in the augmented section because these things are zeros. But then multiplying 1 by -1/2, we'll get a -1/2 here and a -1/2 here. Okay, so we finally have P of B to C. Okay, it's that mess. So we're going to take that mess oh, that's not a 2. Don't know what that was. Okay, we're going to multiply by that vector we had earlier, 15, 20, 0. Okay, so we have 15 times 1/2, 1/2, 0, plus a 20, 1/2, -1/2, 0. We don't need to worry about the other one because it was 0. So we get a 15 halves, 0, plus a 20 times, so we get a 10, or we can actually just write this as a 20 over 2, -20 over 2, 0. Okay, so we'll get a 35 over 2, we get a -5 over 2, and we get 0. And there you go. That right there is your x vector, or your x coordinate relative to C. Okay? So, it is a lengthy process to go find your change of coordinates matrix, right? That's why it's kind of the hardest part. It's definitely also easy to make a mistake in your addition and in your subtraction and all that stuff. But at least you get the problem done, I guess. Yeah. All right, second to last problem. We have in P1, let B be, this is a basis, 8 plus 7t and 9 plus 8t. And we have C, that's 6 plus 5t and 7 plus 6t. We want to find our change of coordinates matrix from B to C and find the change of coordinates matrix from C to B. So this is the exact same thing that we did in problem 23. Okay, so now we're really just mastering getting our change of coordinates matrix just like that. All right, so what we're gonna have to do here, and notice that our change of coordinates matrices are going to be 2 by 2. And remember what I said about the inverse thing earlier. If we invert one, we'll get the other. So actually, we're only gonna have to find one of these, and then it's gonna be pretty easy to find the other one. Okay, so let's get started. So let's do our B matrix, okay, and that'll be 9, 8. We'll augment that with 6, 5, 7, 6. This actually looks like it's going to be pretty nasty to row reduce, right? But it actually won't be, and it's kind of, if you get something like this, if you're given something like this on a test, I really don't think anybody's going to give you something like that you actually have to go through and do disgusting row reduction to get. Unless you're given like a calculator or something, and still I think it's a pretty harsh problem because it's really tedious and it doesn't test you on any linear algebra stuff. So get kind of suspicious when you have something like this, because there's a much easier way to do that than to do this than like going through and doing, okay, how do I zero out 7 with 8? That's not what we have to do here. What we do have to do here is we can just subtract the second row from the first row. Okay, so if we do that, right, if R2 now becomes R1, and actually that's not what, we can't replace like that. We'd have to do R1 equaling R1 minus R2. There we go. That's something that we can do. Okay, and so if that happens, well, what's 8 minus 7? It's 1. 9 minus 8, 1. 6 minus 5, 1. 7 minus 6, 1. And then we have 7, 8, 5, 6 on the bottom. So you can row reduce to make something nicer. You don't have to necessarily like zero something out when you row reduce. So it's an interesting tactic, and that's why I really wanted to show you guys this. Okay, so anyways, I don't know why I just erased that because that's important. But we're going to actually start to row reduce now, which will make it's going to be a lot easier now than it would have been before. If we want to zero this 7 out, multiply this top row by -7 and add. So we would get a 1 here. We would get a negative, this would be -2, and this will be a -1. Okay, and then this thing would become a 1, 0. To zero that thing out, that's not a 6, that's a 0. Jeez. Learn to write, God. So this is -2, -1. What goes here? Well, to zero this thing out, you have to multiply by -1 and add. So multiplying this -2 by -1, you get a 2. Add, you get a 3. And you would end up getting a 2 here. Okay? So what did we just find on this side? Well, we had B on this side and C on this side. Okay? So we now found a change of coordinates matrix from C to B. Okay? And that was 3, 2, -2, -1. Now we can find the change of coordinates matrix. Actually, I'll write like this. We can find this by just taking the inverse of the change of coordinates matrix from C to B. Okay? This will just be -1, 3. We switch those two, and then we negate the others. Okay, so we found this now. Oops, I'll circle the whole thing. Found this, we're done. Okay, now let's move on to our final problem for this video. All right, so last problem here, problem 25. We have a vector space that is in R2. Okay, vector space V is equal to R2. And we have two bases. We have B and C. B is defined by 2, 1, and 1, 1. And then we have C, which is defined as 3, 1, and B2, and 5, 2. I don't know why I call that a B. Okay, so we're asked two things. We're asked to find 2, 1 relative to B and 2, 1 relative to C. To find 2, 1 relative to B, it's actually pretty easy because there's a 2, 1 right in the basis B. So you can actually just write this as, well, 1 of these and 0 of these. So you can put the 1 there and the 0 here. Okay, so it actually works out really nice. But for 2, 1 relative to C, how do you do it? Well, you could go through that basis B, right? But I mean, like, neither of these bases are the standard basis. So you can go through basis B, but what I would do, because it's going to be easier, is go through basis, the standard basis anyway. Okay, what I would do is, well, 2, 1 relative to C. 2, 1 itself is relative to E, right? Because you're trying to find what 2, 1 is relative to C. You're trying to find this, but you know that 2, 1, these are coordinates of the standard, relative to the standard basis, right? So you're trying to, I mean, let me even graph this out to hammer that point home even more. You're going over 2, and you're going up 1, and you have a vector here. And you want to find what this vector is pointing to relative to C, right? So, you know, maybe with C, your y-axis is doing something like this. And now everything's different. So what we need to do here, we can establish a change of coordinates matrix, right? Because we know here that since these two vectors here are relative to the standard basis, right? That's how we're defining our new basis. That's how you're always going to see the new basis defined, most likely. We know that, and from the change of coordinates section as well, that this is the standard matrix from C to E, right? Because this is how you get C from E. That's kind of essentially what this is saying. So this would be 3, 1, 5, 2. But that's not what we want here, because we want the change of coordinates matrix from E to C. Okay? And the reason why is because we can multiply by that change of coordinates vector relative to, the coordinate vector relative to E, and we get the coordinate vector relative to C. Right? We get 2, 1, C. Okay? So, how do we find the change of coordinates matrix from E to C? Well, what we do is, this is just the inverse of this matrix, so we invert it. We have a 2, a 3, and this is negative. So we just multiply this by 2, 1, and we'll get our answer. So we have 2 times 2, negative 1, and then we have a 1 times 5, negative 3. And this is equal to, we have a 4, this will become a 4, minus 5 is negative 1, and we have a 2 times negative 1 is negative 1, plus a 3 is, let's see, negative 2 plus 3, sorry. Negative 2 plus 3 gives us a 1, and there you go. You have your answer. Okay? So that is going to do it for this video. That has been pretty much everything past determinants that you learn in linear algebra, except for the eigenstuff, which will be the part 3 video. So I really hope you're enjoying this series so far, and I really hope that, of course, the part 3 video will help you just as much. Okay, definitely subscribe to the channel for more content, and share the video. You know, if you have other students in your class or in other linear algebra classes that could definitely use a review like this, definitely pass it on. I would really appreciate it. Of course, you know, trying to get to that 1K sub mark, so we'll see. But anyways, thanks for watching, and I'll see you soon.